So everyone uses this curve, but very few actually understands it. So today I will show you that kernel density estimation, aka KDE, is not some magic. It is just addition. Okay. Suppose I give you some data point. This is a data set which consists of numerical data points, that is numerical values. Okay. And we want to know the shape of the distribution, that is where the data is dense, where it is rare. Okay. So traditionally, what we will going to use? We will use a histogram, right? We want to know the distribution of a numerical data set. So we will use a histogram. Okay. But histograms has some problems. What problems they have? They are blocky. Each the data point is represented as blocks. Okay. So they depend on bin width. If we change the bin width, the histogram will look different. And they change if I shift bins. Okay. Same data but different pictures. If let's say we have a data set and we give two different person to draw the histogram of this data set, so definitely most of the times the histogram is going to look different. Okay. So let's take an example of this data set and draw its histogram and see what problems we will face with histograms. Okay. So in the first case, we have taken 5 number of bins and we draw a histogram. In the second case, we have taken 10 number of bins and then we draw a histogram. So we can clearly see that the two histograms are looking completely different. So we can say histogram will not give a consistent representation of distribution if we change parameters like bin width or number of bins. Okay. So this is where KDE comes in. KDE is also a representation of distribution of a data set, just like a histogram. So in KDE, instead of counting data points in bins or intervals, KDE does something smarter. Each data point becomes a small smooth hill, and we call this a small smooth hill as a kernel. And now just add all these hills, and then we'll get a KDE curve. Okay. So let's take a data set. Okay. And we will draw a KDE curve of this data set from scratch. Okay. So now for each data point, what KDE will do? KDE will draw a small smooth hill, and these small smooth hills are called kernels. Okay. And now what KDE does is that it will add all these small hills, all these kernels into a single curve, which is called the KDE curve. So now this is the KDE curve. Now how these kernels, these small hills, are added into a single KDE curve. To understand this, we will look into the example of the same data set. Okay. So these are the three kernels. Okay. Which are representing the three data points of the data set. So for simplicity in understanding, I have drawn these three kernels into two separate coordinate planes. Cool. So the vertical lines in each kernel, that is the orange one in the first kernel, the purple one in the second kernel, and the blue one in the third kernel, are representing the height of the kernels at respective points. Okay. So now this is the final KDE curve, and the height of the KDE curve at any x is the sum of the heights of all the kernels at that x which are coinciding. So these vertical strip are representing the height of the KDE curve, which is the summation of the height of coinciding kernels at respective points. Okay. So now let's look into the formula. This is the formula, and so this is the equation of KDE curve. It simply means that pick any x, plug it into this formula, you get one number. That number is how high the KDE curve is at that x, which is also the density value at that x. So in this formula, uh, let's look into these two terms, the bandwidth and the kernel function. So now let's look at the bandwidth. Bandwidth is simply the size of the kernel. That is, if we have a small bandwidth, then the kernel will become narrower and taller. But if we have a large bandwidth, then the kernel becomes wider and shorter. So in a way we can say that bandwidth decides how far a point's influence reaches. Okay. So this is the KDE curve of the same dataset. The example we have taken earlier, this is the KDE curve of the same dataset. Okay. uh, and this is the KDE curve by taking bandwidth as 0.1. Now let's increase the bandwidth and see what how the KDE curve is going to look. Now here we increase the bandwidth to 0.5. So this is how the KDE curve looks. If we increase the KDE curve even for bandwidth even further to 1, this is how the KDE curve will be. And for h is equals to 2, this is how the KDE curve will be. Okay, now let's look at the kernel function. Now the kernel function is represent the shape of the kernel. Bandwidth decides the size of the kernel, and kernel function decides the shape of the kernel. Okay, and uh, in most of the cases we are going to use a Gaussian kernel, which is like a bell curve. This is the formula of the Gaussian kernel. Okay, other types of kernel are uh, first one is uniform kernel, then we have Nepachnikov kernel, then triangular kernel, etc. So now keep this thing in mind that the choice of kernel matters less than bandwidth. Okay, so yeah, this is it for today. And if you have any doubt related to KDE, you can leave a comment and we will meet in the next video. So thank you.